another assignment available, and we will be having an exam in a few weeks. So there'll be one more, but there'll be one more problem set before the exam. Okay, we'll talk more about that as time approaches. All right. So let's see. So last time we were talking about one application of perturbation theory, looking at a situation where we have some matter in the presence of an external electric field, and that causes a change in the energy levels. Forces due to the external field are in addition to the internal forces on the material. So in particular, we're looking at this for the example of hydrogen. Okay? So we're looking at how the energy levels are perturbed by the addition of the external electric field. And so the Hamiltonian has this form. This is the binding energy of the electron to the proton, and then the interaction with the external electric field. Okay? And this is a perturbation when the energy scale associated with the internal, in terms of the energy scale associated with the perturbation is small compared to the energy scale associated with the internal binding. Okay? So we're going to put some limit on E when E is too big. This is not a perturbation anymore. And that is equivalent to saying that E, the electric field, is small compared to what we would call the internal electric field that the electron is experiencing due to the proton. Okay? So, and that, of course, as we discussed, this is a huge electric field, and so this is an excellent approximation for any static field we would generally put on that system. Okay? The case we're looking at right now is what you might call the DC Stark effect. We're talking about a constant electric field. In your homework, you're looking at the case of what we call the AC Stark effect, where we're applying oscillating fields. A little more, that's actually in general a much more complicated problem. We're talking here right now about time-independent perturbation theory, where we have some Hamiltonian that is so independent of time, right? When you have a time-dependent Hamiltonian, well, things are more complicated. And as you know, the effects of those perturbations can be to drive the system from one level to another. You can have absorption and emission, right? So we'll come to that probably at the end of the semester. But as you'll see in your homework, under certain circumstances, we can take the time-dependent Hamiltonian and transform it into a time-independent Hamiltonian, and then get an the effect of the applied oscillating field is not only to drive population in absorption emission, but also to shift levels in the same way that a DC field will. Okay? So that's just a little bit of background in terms of thinking about the problem that you have currently for homework. All right? So that's the problem. And what we showed last time, well, firstly, the lowest order shift, the first order shift in the energy for any of the stationary states labeled by NLM is going to be 0. Because those states are eigenstates of parity, whereas the dipole operator is an odd operator in parity. So it can connect two states that have the same parity. Now, in particular, this state, the ground state is spherically symmetric, and so it's completely obvious that you can't have a mean dipole. But that would be true also for a p state. Okay? I mean, a p state, if you look at it, if you look at, say, one of the orbitals, say, it looks like this, well, there's the probability amplitude here is negative that, so the probability of the electron here is the same as the probability of the electron there. So there's no, on average, no dipole moment. Okay? Or in any state that is got definite MLM, or elementary station. Okay? So, and we could use our non-degenerate perturbation theory in the case of the ground state because it's not a degenerate state. Okay? So we went to the next highest order perturbation. That's second order. And this is our general expression for the shift. Depends on the off-diagonal matrix element between the state we're looking at the perturbation of and all the other states, in this case, all the excited states of hydrogen, over the energy denominator. And for the particular case at hand, we're looking at, we're calling the direction of the applied field the z-axis. Okay? So we have studied a selection rule that happens in that case. Firstly, we always have it to be true no matter whether this was x, y, or z, that the matrix element vanishes unless the difference between the L's is plus or minus 1. Okay? And that is an example of a selection rule coming from the fact that this is a vector. You'll see that. This is a rank 1 tensor. As we'll see, this is an example of the Wigner-Eckhart theorem. Okay? But we saw that in our homework that we just handed in. And in addition, because this is along the z-axis, the only non-vanishing matrix elements are the ones with m equals 0, if this started in m equals 0. This is an example of a selection. It's an example of the dipole selection, which we'll study in more detail. So we only have to sum over all the p states. These are p states with m equals 0, and this is the ground state with m equals 0. Those are the matrix elements we have to sum over, and then we have the denominator here. That should be squared. Okay? And that sum can actually be done, and you get this result. Okay? And if you were, had a gun to your head, that's what I'm going to do now, but just hypothetically, and someone asked you, estimate what is the ground state shift of hydrogen due to a Stark effect, you should be able to do that within a factor of 10. Okay? Just dimensionally. Just because dimensionally. And this is it. You know that there's no first order shift. And the second order shift has to be of the order, the characteristic energy scale H1 squared over the energy denominator, which is of the order of the Hartree. Squared over A naught. Right. P squared over A naught. Right? That's the Hartree energy. That's the energy denominator. And this is H1. And so that energy scale is the electric field scale squared A cubed. And that's what we get. The rest of it is details. Everyone clear on that kind of analysis? One everyone should learn how to do. Right. So this is what we call, this is what is known as the quadratic Stark shift. It's quadratic because the shift in the spectrum, if you looked at the spectral lines in a spectrometer as a function of the applied field, then the shift would change as the second power. It's quadratic with the applied field. So that's why it's called the quadratic Stark shift. Okay? I mean, these things were seen empirically in the early 20th century, well before, well, not that far before, pushing the war out and kind of solved it, but it was.
And how far could we push that approximation? Now, if you'll ask what is the fourth order?
Sure, they're all, I mean, that's the scale. It's all the same. Absolutely. It's all, it has to be. There's no other units in the problem, so it has to be that. I mean, the prefactor, whether it's going to be of order 1, of order 10, you know, there can be symmetries, things can vanish, right? So in this case, the 0th order was 0. I mean, the first order correction was 0, whereas you would have said that it's of order this, the first order.
Is it true for any other orders?
Yeah.
Okay.
Right, because of parity. Indeed. So all the all orders vanish. So you have to, you know, use some other physical pieces of reasoning to get at it. But in terms of the scale, it's going to be that if there's a non-zero prefactor, it'll be of the order h1 to the power this over that in some power. All right. So what we were saying at the end of the lecture is that we can understand this even further in physical picture by thinking about what's going on. Why is it that we have this kind of quadratic dependence? Just thinking about this from a physical picture. Well, what we said is, if we looked at this in 0th order, we have our hydrogen atom, which has no electric dipole moment for the case of the ground state, because the electron is in an S state and it has no mean position relative to the proton. Okay? And then we apply an electric field. Let's say we apply an electric field in this direction. What happens is, well, the electron wave packet will sort of shift up a little bit. So its center is here now. Okay? And so there is an induced dipole moment. And that induced dipole moment is aligned with the field. And because it is aligned with the field, this is positive, which means the energy is lowered, right? So there will be a shift in the energy. So there is an energy level associated with there's an energy shift associated with the induced dipole moment interacting with the field. Now, the induced dipole moment is proportional to the field by something we call the polarizability. How much of a dipole you induce, it's how polarizable it is. Okay? And then there is an interaction energy of the induced dipole moment with the field. And what is that energy?
It's like minus d dot e.
Close, but not quite a cigar. It's actually, if you we'll review this thing right now, it's a half of that. I'm sure you've seen that. Even glance at maybe in Griffiths or something like that. Let's remind ourselves where that comes from. I mean, factor 2 are friends, it's not a big deal, it's basically that, and that's, so it's base, but this is, you know, going to be minus a half alpha e squared. There's your quadratic shift. But this is the actual correct classical answer. So where does that half come from? Well, let's just take a little classical picture here. So let's just think about a charge on a spring. Okay? And now we apply this electric field. And the electron moves. Okay? So the electron, the spring spreads down a little bit. Here it is. And there's some shift. Right? So it's pulled. Right? And that pulling is a balancing of the applied force with the restoring force. So whatever the spring constant is times the induced this force has to balance this force. Okay, that's the restoring force. And kappa, of course, is related to the oscillation frequency. Right, so now we have Z induced. That's what our equilibrium position is. Okay, so now what is the total energy, potential energy stored in the system? There is the potential energy that is now stored in the spring, plus the interaction energy of this induced dipole moment with the external field. So the total energy of the system is 1/2 m omega squared Z induced squared minus D induced times the electric field. Okay? So you put that D induced is equal to dZ induced times the electric field, in this case in the Z direction. And you put that in here, and half of that cancels half of that. So this becomes minus a half D induced times Z. That's where that comes from. Okay, yeah.
Would you get the same answer if you said initially there wasn't any energy stored, and the energy that's stored is the work that the field did in stretching out this?
Yeah. So the question is, let me think about this carefully. There is why I don't have a solid answer in my mind about this is the question of potential energy associated with configuring the charge configuration. Now that's the energy stored in the field itself rather than the energy stored in the interaction between them. So I think what you're saying, Adrian, is correct. Why I'm hedging, and I'm trying to think about what the precise way to say this is of course, there's two energies. There's the energy associated with how much work it does to stretch the spring. That's this. Okay. Now there's another energy associated with the interaction of the charges with the fields. So that's the potential energy that the charge has that can be released to do other work. But it seems like what you're saying makes sense, and I don't see where I'm missing something. So I'll have to come back and think about it. I don't have a clear answer. I gotta go back to freshman physics. Sorry.
Me too.
All right, but this is correct, and this, as we said, the induced dipole moment is proportional to the electric field, right? The Z induced here, or the induced dipole moment we said was this, which is E squared over M omega squared times the electric field. This is the polarizability in this simple Lorentz oscillator model. Okay? It's a positive number. So this energy is lowered. Okay?
You're doing our homework for us.
Yeah, some of it.
Can you do more of it?
I can,
Will you?
maybe. All right. So, let's see where we're going with this. Right. So, how does this compare with the quantum mechanical expression? Well, I claim it's exactly the same up to what the polarizability is. That's to say the physics is exactly the same. We are perturbing the system by inducing a dipole moment. That induced dipole moment is proportional to the electric field, and that induced dipole moment then interacts with the field to give a quadratic effect. Okay? So what is the induced dipole moment here? There is no dipole moment in zeroth order, right? But there is a dipole moment that is induced. How would we calculate it? Any thoughts?
Would you want some sort of charge distribution or figure out, or probability distribution of the charge?
Yeah, I mean, clearly what happens here is that this, what the hell do you call this thing? The electron cloud has been perturbed in some way. So how are we going to calculate the perturbed electron cloud?
You could compare the second order shift with the 9/4 with the -1/2 alpha E squared.
Sure, I mean, we could work backwards from this. That will work. But I want to go forward. I say I don't have this. I want to say, how can I calculate what D induced is? Just based on the idea, I want to calculate how this electron cloud is perturbed.
Is it related to the first perturbation in the state?
Exactly. So we need the perturbed state. The state is perturbed. And that gives us a first order. So this is the, I'll call it U1s tilde. This is the perturbed state. Now, of course, this is not pure S state anymore. It has a superposition of S with P, right? So the perturbed to first order, this is equal to the zeroth order state plus the sum over all n prime, the excited states, not equal to 1, times n L equals 1, n equals 0, n prime 1, 0, times H1 and L sorry, 1 and 0, 0 divided by E. And that's minus E D. Right? That's what we had for perturbation theory. We get a superposition of the 0th order one with all the other energy levels. This is, of course, unnormalized by an amount that depends on the off-diagonal matrix element between the state we're perturbing, in this case the 1s state, and then the excited states. And it would be all excited states, but it's the same matrix element, and so only the p states survive. Yeah?
So then should we divide by the U1s tilde with itself for D and G?
Ultimately, we're going to have to renormalize. Yeah. So the
Just to make sure, so the expectation value of U1s tilde with H, I mean, the expectation value of H with respect to US1 tilde is 0, right? Because it's the first order energy?
no, that is not correct. That will have, it depends to what order we keep.
Up to order
Up to order 1.
1, yeah.
Yeah, but because this, right, because this term will be 0. Will be shifted. But, I mean, but, because this, I mean, if you looked at that U1 tilde, you took the expectation value here, then this thing only has diagonal matrix elements in the 0th order guy. And then there's this.
Yeah.
But this is already first order.
Yeah.
So it won't have any contributions there.
Yeah.
So that doesn't count. Of course, then it gives a second order contribution.
Yeah.
That was the other way that I showed you could do the perturbation theory by taking the expectation value and keeping all the terms to a consistent order in the perturbation. All right, so we can do that. So now we can look at the induced dipole moment. In this guy. And we're just going to look at the induced dipole moment along the z direction.
It's not an operator, is it?
No, it's not. Thank you. So this is we need to renormalize. Okay. All right, so now I want to find the lowest non-vanishing contribution to this, okay? The first, in the lowest order in the perturbation. So this is of order 1, this correction term. In the denominator, when I take the inner product of this with itself, I'm going to get something of order 0 and then something of order 2. Right? This is quadratic when I square it. So to first order, I can ignore this. Okay? And so then what I get is the following. The only non-zero matrix elements are the off-diagonal ones. All the diagonal ones of this or this are 0 because of the parity selection rule. Okay? So the parity selection rule, again, this is really the parity selection rule tells me that I can only have off-diagonal matrix elements between states that have L that differ by 1. Okay? So when I plug that in, what I get is the following. This is equal to minus E. I have the sum over all n prime not equal to 1, n prime 1, 0, z 1, 0, 0 divided by P n prime P minus B1s plus the conjugate. All right, so that's to first order. This is the induced dipole moment. All right, so now I can say, let's see, what do I say? This induced dipole moment. I left out stuff. I left out this. It's an important term, pardon me. Something is wrong here. Pardon me. What's H1? H1 is minus E, or it's E times electric field times E, right? That's H1. I forgot that term. So there's an E squared here. Right? And then I have this term again. Plus the compound conjugate. Okay. So that's just I forgot that when I plugged in this, which is how it should be. Right. So what I see here is that, did I get all the signs right? I think I did. Yeah, check out.
The normalization is 0 to first order or 1 to first order?
It's 1, I'm sorry, it's 1 to first order. Right? What I meant to say is this piece is all right. Oh, I see where I got it wrong. This is 1s. And now it's the right sign. Now I feel better.
Wouldn't it be easier to just put it inside of absolute value so you can't make that mistake?
So you do it the way you think works best. So the bottom line here is that this is equal to, as just before, is proportional to the electric field, and we have the polarizability calculated in perturbation theory is 2e squared, those two terms are equal, because that actually is real, times the sum over n prime, not equal to 1, times this matrix element. Okay. So what we've calculated using perturbation theory is how the atom gets an induced dipole moment, and this is the polarizability. Okay? So now let's just consider minus a half the polarizability. I'll call this the quantum polarizability times the electric field squared. Well, that's exactly what we have over here. Exactly. So this is equal to the second order perturbation on the 1s. It's exactly the same physics.
Should that be 1s minus n+?
No, there's a minus sign out there somewhere. Right? That minus sign is here. So, because this is a positive number. It must be. So it's exactly the same physics. The only difference is the polarizability quantum is different from the polarizability that we have classically, which we just calculated for the simple Lorentz oscillator to be this. And so, Stephen, I will do a little more piece of your homework as you suggest, and here it is. We can define something which we call the oscillator strength. F as the ratio of the polarizability we get from our quantum mechanical calculation compared to what we get classically. All right? And what we see is that is equal to 2m omega squared divided by times this matrix element. I'll write it this way. G is the ground state, E's are excited states. Okay. Or where h bar omega EG, the omega EG is the Bohr energy associated with this energy difference. Okay? So this kind of picture, if I think about this as in the following way, that there is actually a different resonance frequency associated with every different transition from every ground state to every excited state. That I could think about these as different oscillators, and choose this, make a Lorentz oscillator, a charge on a spring, that's a harmonic oscillator that has the same resonance frequency as this transition. Then what I see here is that F for a given transition with frequency omega EG, set that equal to the simple harmonic oscillator frequency. Then I have the oscillator strength associated with that excited state, and it is 2n EG over h bar times this. That is known as the oscillator strength associated with that transition. Yeah?
Where's the 2 come from for the alpha?
It came from the fact that I had two factors. This plus this complex conjugate. All right? Yeah?
Why is the H bar downstairs? Outside of the sum?
It shouldn't be there. There is none. Sorry, that's this H bar.
Yeah.
Pardon me. Yep. All right. The point here that I want to emphasize is how to interpret this. How do we interpret this? Well, you may recognize this. That combination for a harmonic oscillator of frequency omega. Maybe not. This is just the characteristic length scale associated with the harmonic oscillator. In fact, this is the ground state width. This is for a simple harmonic oscillator. So what the oscillator strength is telling us is that this isn't really a harmonic oscillator. If it was a harmonic oscillator, this would be 1. There's something associated with the orbitals, some mean squared length associated with the orbital. Comparing that to the harmonic oscillator tells us, in some sense, how different this is from a simple harmonic oscillator. This isn't a charge on a spring. It's these two energy levels. But historically, the famous Lorentz made this model of what was going on with atoms and saying, you know, well, what's going on is we have electrons. People had discovered electrons, but they hadn't yet thought about the Bohr atom, and the electrons are just bound to the nucleus. If you know about the nucleus, again, Rutherford, they're kind of bound in a harmonic potential, and try to model and explain the spectra of atoms based on that model. That was called the Lorentz oscillator model. And we get pretty far with that, except that we find that the strength of the different transitions is not quite what we expect, and he threw in some fudge factor, which he called the oscillator strength. But now we can derive that. We see it is effectively just like a charge on a spring, but with a polarizability that's not the polarizability of a charge on a spring, but is darn close to it by an amount that this is this factor. And the strength of the transition, if you like, depends on the oscillator strength. Yes?
The strength of the transition, does that mean like what transition is more likely to occur, or like what is the strength itself?
Yeah, so what the strength of the transition will mean is how big is that matrix element for a given, say in this case, for a given ground state and excited state. So what that means physically, for example, is if I had in this sum, the biggest contributions are where these matrix elements are the biggest. So the amount of how much this S state is perturbed by the excited state depends on the strength of this transition. It turns out that for example, in hydrogen or in generally the atoms, the most of the oscillator strength is in the first transition. The second excited states are less strong, etc. And what that would also mean is, for example, if I were to apply a laser beam that was resonant with these different transitions, that I would need to apply much more power in this transition compared to this transition in order to drive it. This is a much stronger transition than this one. So I require less perturbation to make this transition happen than that one, for example. It would also mean that if I started my atom in the state and it decayed, that this is going to happen much faster than this, because this is a much stronger transition than this one. And that's all characterized by this matrix element. All right, very good. So, so that's just something to keep in mind, that there is, the same physics going on, even though we're talking about quantum mechanics and wave functions. It's still just, an electric field is pulling charges apart and making a dipole moment, and that dipole moment interacts with the field. It's just what the specific value of the polarizability is different from quantum mechanics compared to classical mechanics. All righty. So, well, this was for the ground state. What's the stark shift on the first excited state of hydrogen? Well, now we have to worry about the fact that we have degeneracies, right? And this quadratic stark shift will blow up in that case. So something we have to now think about degenerate perturbation theory. So we got into trouble here because of the energy denominators, right? So we've seen in second order for a given level here that the energy shift we wrote like this. And when we have two levels that are the same energy, or close to it, then that's going to screw up. Okay. Now, so how are we going to deal with that? So let's consider, suppose we have degeneracies. That is to say that there are stationary states now that are specified by at least one other quantum number, such that H0 on this is En0 for all alpha. Alpha is just some other quantum number, like N and L. Okay? So the energy only depends on N, but it doesn't depend on alpha. Like in hydrogen, alpha could be L and N. All right? So the way we can deal with this is the following. Because what we have here is we have a subspace of dimension G sub n. Where G sub n is the degeneracy. For hydrogen, this is n squared in the absence of spin, right? For each energy. So, in formulating the perturbation theory, the idea then is to pick the states that are the zeroth order solution of the problem appropriately so that we can get rid of any divergences. I'll show you how that works. Remember, if I take the I don't want to give like this. If I take any superposition of the zeroth order, I should label them as such. These are zeroth order eigenstates of the H0. Okay. If I take any superposition of these, this is also an eigenstate with exactly the same energy eigenvalue, right? So on these new guys, labeled by I, this is also an eigenstate with exactly the same energy, because I took a superposition of states that were all degenerate, that all had the same energy. So the trick is how to choose this so that we don't run into problems, and here's how you do it. So we choose these guys with labeled by I. We choose these such that the following is true. These should be, remember we had chosen previously for different energy eigenstates, we chose the perturbations such that they were orthogonal for different energy levels. But now we're going to do that within a given energy space. We want this to be 0 if I not okay. Remember, we had chosen previously when we looked at this in the non-degenerate case, we said this was, say, the 0th order state thought about as a vector Hilbert space. And then we chose the perturbation orthogonal to it. Okay? I want to make sure that the perturbation is orthogonal within a degenerate subspace. That's what I want to make sure is true. So, how does that save us? Well, let's look at our perturbation series.
So do you want U and I to be orthogonal to all the U and alphas? So that's a superposition of like the U and I, 0?
Indeed they should, but in particular, it's for this particular when I not equal to I prime. Okay, so that's important. Let me get my notes here, just to make sure I'm not screwing something up. Yeah, no, it actually be true for all I. For all I. So let's see how that works. So I'm going to start with my perturbation series. So we have H0 plus acting on this is my first order piece of that, plus H1 times Ni0 should equal E N0 U N I1 plus E N1 U N I0. This can depend on I. So this is a first order piece of the Schrodinger equation, right? This is a first order piece, and this is a first order piece. Equals, this is a first order piece, and this is a first order piece. All right, so now let me take the inner product of this with what? Okay. So now I'm going to take this with UN0 prime. So I just took the inner product of this equation with another eigenstate in the same subspace. Okay? So what can we say about that? Well, this is an eigenvector of this with eigenvalue en0. Right?
Yeah.
This cancels this. Before, we had taken the inner product with a different m, that, or an n prime, associated with a different energy. But now these have the same energy within the same degenerate space, and they cancel. Okay? So, what we see here, if we've chosen this appropriately, is that we can solve for this. These guys are different states within the same subspace, and we can choose those to be orthogonal. So we can choose this to just be two other orthogonal states. We've just done a change of basis. These guys were an orthonormal basis in the space. We've just done a change of basis to another basis in the same degenerate subspace. Okay? And so what we end up with is the following. We require the new eigenstates of the system that we're going to call the zeroth order eigenstates to be ones that within a degenerate subspace, the matrix elements in that basis are this. Well, what does that say?
It's diagonal.
It's diagonal. So it says that in order to properly account for all of the perturbations, so all appropriate orders within a degenerate subspace, what we should do is simultaneously diagonalize the whole Hamiltonian in a subspace with the same energy in 0. Once we've done that, we've gotten rid of our problem children, and everything converges. So for example, in hydrogen, which we'll now study, the Stark effect in hydrogen. So, we have the 1s state. Then we have the 2 states. We have the 2s state. And then we have these 3 2p states with ml equals -1, 0, +1, and this is an equals 0 state. So this is a 4-dimensional space. What the degenerate perturbation theory tells us is that in order to account for the perturbations self-consistently, what we should do is just diagonalize the Hamiltonian in the subspace. We have this Hamiltonian. Remember, what we're actually trying to do is diagonalize this. That's what we really like to do. We'd really like to find the eigenstates of the whole Hamiltonian, right? What perturbation theory told us is, well, instead of diagonalizing the whole Hamiltonian, I can tell you how the diagonal matrix, the diagonal elements of this are perturbed in terms of matrix elements of this. What this tells us is that when we have degeneracies, this guy is going to, well, H0 is going to be block diagonal, right? And then we look at each block, block by block, we diagonalize within a block. That gives us the first order corrections. And then we use those to go to higher orders, which almost never do, unless it vanishes. Okay? So that's the key. The key idea here is that we block diagonalize, and that gives us the first order corrections. So let's do it for the case of the Stark effect.
So,
Yeah.
just to make sure, so we never had, also when we had a degeneracy, we didn't see the problem at E1, right? At the first order in the energy, we didn't see that problem.
We don't.
So
It comes in if I were to look at the
State.
perturbation of the state.
yeah,
Right.
the first order of the state.
Mhm.
So, and here, so what would we use for E1s minus E? I mean, here
Sure.
it won't be 1s,
So-
but you know.
To see that detail, which I wanted to slough over, but I can see it. Remember what we have to do. Remember how we did that. So let's go back over here. What we had done is, in order to, we wrote UN1 before in terms of the superposition of all the other UN0, UN0, UN1, right? We
Yeah.
wrote a complete set, summed over
Yeah.
all those guys, and we plugged that in. Now we have to think about summing over both N and alpha or N and I. And then look at what that superposition is. However, using this fact, what we will see is all the terms that were degenerate
Mhm.
with the same N
Mhm.
don't appear.
Mhm.
And so we never have energy denominators between two states
With
that
the-
have the same energy.
Okay.
And so it goes away.
So yeah. Okay. Thanks.
All right, so let's look at this for the case of the Stark effect. So let's look at this in the particular subspace with principal quantum number n equals 2, right? There are fourfold degenerate. So in principle, we have to diagonalize a 4x4 matrix, okay, in order to get the first order correction to the energy. There are those four states. We have the 2s state, which only has m equals 0, and then we have the 2p with ml equals -1, 0, and +1. Those are the four states. Okay. So we need to diagonalize that matrix, right? All right. However, selection rules, right? H1 is equal to E, Z, Z hat, right? So, we know from the selection rules that this vanishes unless what?
M prime equals M.
Right. So we have to have, this can only connect, the only matrix elements are off diagonal, first of all, between S and P. There's no, within a given subspace with a given L, all those matrix elements vanish because they have the same L. And we have to change L by plus or minus 1. All right? So there's only off diagonal elements in this problem, firstly, and they're off diagonal between the S manifold and the P manifold. But that's not the only selection rule. M, right? Because this has M equals 0, there's only one non-zero matrix element and its conjugate. The one between this and this. Is that clear to everybody? Right? So the only non-biselection rules only non-vanishing matrix element is 2s h1 2p 0 and conjugate. All the other matrix elements in that four-dimensional space vanish. Okay? So with that said, we can write this in, it's really only a 2x2 block that I care about. That is to say, I should order my basis vectors appropriately so that I have a 2x2 block between these two states, and then a 2x2 block with the other states, and that's all 0. So H1 in this basis, first of all, I'll order the states so that the 2s is here, the 2p with m equals 0 is here, and then there's the 2p with m equals plus 1, and the 2p with n equals minus 1. Those are my four basis states in this n equals 2 subspace. All these matrix elements are 0. All these matrix elements are 0. All these matrix elements are 0. The diagonal ones are 0. The only ones that are non-zero are these guys, the off-diagonal elements between this and this. Let me call that epsilon. Okay? And epsilon star. All right? So we just have to calculate that, firstly. This actually turns out to be a real number. We do it exactly the same way that we have done before. We write this as a wave mechanical matrix element in terms of the radial wave functions and the YLMs. We wrote Z here as square root of 4 over 4 pi over 3 r y1 0 theta 5. We do the radial integral, I'm sorry, y0 0. No, y1 0. We do the radial integral, the angular integral, and then I gotta look up what the number is because I don't remember it.
I think this was exactly in the last homework with Z, X, and Y. For
Right.
all the
There's some,
possible
so yeah. Yeah, somebody actually thought ahead of what might happen in lecture and maybe do the right thing sometimes. Anyway, this is equal to minus 3 e z a naught. Okay? It's a real number, so I'm going to get rid of the star.
Do you think a real test still have a star?
It could, but I want to make the fact that this is, if e star equals e, that it's real. Because then I could diagonalize this by I. Right? So what are the eigenvalues and eigenvectors? So let's go to the front board. Even if it was a star, we could do it, but it's more complicated.
Are they plus and minus epsilon?
Yes, they are. Because we know, in this case, so the eigenvalues and eigenvectors of this matrix. It's the only matrix we have to diagonalize. Well, this is epsilon times sigma x of a pseudo spin, if you like, associated with two states. And that has nothing to do with spin of the electron, it's just two states. It's a qubit, if you like. And we can diagonalize that. The eigenvalues of the sigmas are plus or minus 1. So the eigenvalues are plus or minus epsilon. Okay? Plus or minus this. And what are the eigenvectors?
2s plus 2p over root 2 and 2s minus 2p over root 2.
Right, the symmetric and anti-symmetric combinations. It's like, remember, spin up along x is spin up along z plus spin down along z. And spin down along x is spin up along x minus spin down along z. And that's what we got. So what we end up with is a symmetric and anti-symmetric combination of these orbitals. It's a very strong mixing of the two orbitals. Unlike where we had non-degenerate case, where we just had a small amount of admixture of, say, the 1s with a little bit of the p states, because it was a non-degenerate case. When you have degeneracy, you have a strong mixing. Okay? And this, of course, is equal to 3 minus what we had here, minus the plus 3 e z a naught. This is what's known as the linear Stark effect. Or linear Stark shift. It's linear because, well, it's first order, right? That's what we expected. And so if I were to look at what the spectrum was, the energies as a function of this, here's the n equals 2 state. What I find is for small f z that I can think about this to first order perturbation, I have these guys are unshifted. And then I have these guys are shifted. I have, this is the a minus state and this is the plus state, which is a superposition. And then the other guy. All right. Now, there's a couple of things I want to say in my grace period, 3 minutes over time. Why is there a first order shift from the same physical picture that we had before? I mean, what we said here, you know, it's the vestiges are still remaining up here, that for any orbital that is defined by L and N, the mean dipole moment is 0. It doesn't matter that this was a p state. There was, this guy has equal probability for the electron to be here or here. There's no displacement of the electron relative to the proton. The mean dipole moment, no matter what state I'm talking about, is 0. So how in the world do we get a first order shift? It seems like the same kind of thing should happen. I should first induce a dipole moment, and that induced dipole moment then interacts, and that's quadratic. But this is linear.
Because working with the P shell?
Well, if it was just a p, as I say, that has 0 mean dipole moment as well.
But we're looking at superpositions of states.
We are, and why is that justified? Well, it has to do with degeneracy, right? Even though this is an eigenstate, this is, say, the 2p, a superposition of 2p and s, 2s, is also an eigenstate with exactly the same energy. So I don't have to think about L being a good quantum number. It's convenient in terms of enumerating the orbitals, but in the absence of any interaction, any superposition is a perfectly good energy eigenstate. And if you look at the probability amplitudes, this has a positive amplitude and this has a negative amplitude. This is not the sign of the charge, this is the sign of the wave function, okay? And if this is positive, you add these together, and what do you get? Well, you get something which is not spherically or parity symmetric. It has more probability amplitude to be up here than down here. So if the proton is in the middle here, now the electron is kind of up here. So to 0th order, without any perturbation, this has a permanent dipole moment. It has a dipole moment that looks like this. To 0th order. And then that 0th order dipole moment of this energy level interacts with the field and makes a first order energy shift. Okay? So this is an example of what we call spontaneous symmetry breaking. We talked about this a little bit last semester. The point is that when you have degeneracies, it is possible to have eigenstates of the Hamiltonian that don't respect the symmetries of that Hamiltonian. So what we had is we had rotational symmetry. As to say, our Hamiltonian for the hydrogen atom is invariant under a rotation. And that rotation meant that we can look for eigenstates of the Hamiltonian, which are also eigenstates of rotation. Yeah?
Is H1 also invariant?
It is not. Right? Because it's what we're, and that's actually a very important point. Right? So let me take one point at a time, come back to H1. Because H0 is rotationally invariant, we can always find eigenstates which are also eigenstates of rotation. So we could look for eigenstates that are eigenstates with L and M. Right? Those are the eigenstates of the rotation. But we can, if we have degeneracies, I can take superpositions of different LNMs, and that's still an eigenstate with the same energy. Now, this is not rotationally invariant, which means it can have a mean dipole moment. Now to your point, Stephen, which is a very important and good one, which is we had degeneracies because there were symmetries. So all of these eigenstates were degenerate because of the symmetry. In particular, we had the rotational symmetry. But now we put on an electric field, and that electric field is in a particular direction. If we look at it in a different way, we can tell what direction we're looking because the electric field points along some actual direction in space. And so we've broken the symmetry. And because we break the symmetry, we break the degeneracies. Yeah?
No, you just answered, sorry.
Yeah. So that's a generic it's a generic feature of perturbation theory. If you have degeneracies, and those degeneracies are not accidental degeneracies, they're arising because of symmetries. If you put on a perturbation, and that perturbing Hamiltonian doesn't share that symmetry, then you will generally break the degeneracy. Now, we don't completely break the degeneracy. Notice there's still some degeneracy left. Well, that's because we still have this axial degeneracy, right? So there's still a rotation around the z-axis. It's not isotropic, but there's still, if I rotate around the z-axis, I can't tell the difference. So m equals plus 1 is the same as m equals minus 1. All right? Some really good physics today, I think. All right, folks, have a good rest of your day. I'll see you later on. Yeah.